Okay, so I suppose I'll start. I welcome the viewers to this problem solving and live interaction session. Good evening. So I welcome you to this problem solving and live interaction session for the subject strength of materials offered by Professor K. Ramesh on the SWAYAM portal. So today we will be discussing the contents of week 4. So I'll just introduce myself. My name is Ganesh Ramaswamy. I'm a doctoral scholar in the Department of Applied Mechanics and Biomedical Engineering at IIT Madras, pursuing PhD under the guidance of Professor K. Ramesh and Professor U. Saravanan from the Civil Engineering Department. So, for those who have not attended the previous sessions, you are free to scan the QR code on the left side. That will take you to a channel where the previous sessions have been uploaded. Or you can also navigate through the SWAYAM portal page where on the bottom left, where July 2024 sessions are uploaded in some link, which is available. So today we'll be discussing the contents of week 4, which is primarily to do with some free surfaces, some nuances of photoelasticity and strain. Hi, Mr. Jayakrishan, good evening. Are you able to hear me all right? Am I audible clearly? Could I just get a confirmation?
Hey, sure. Good evening.
Good
Yes, you
evening.
are audible.
All right, very well. Okay, great. Well, perhaps we'll get along with the discussion, and should we find time midway, we will try to address that also. Not an issue at all.
Sure. Thank you.
Okay, okay. All right. So let's look at the first question, which we have actually done quite a while. In fact, it is a bit related to the topic of discussion as well. So the question says, a bar of a bar of cross section 40 by 2 mm is loaded with 100 Newton along its length 150 mm as shown. So there is a rectangular bar which is loaded axially along its length, and its cross section is rectangular. So basically we have this as 40 mm. And this is some 2 mm. And this we will see when we cut a section like that and view it. And it is 150 mm long, and it has been loaded with 100 Newton. So this load is 100 Newton on either ends. So the magnitude of the stress vector at point D on a plane whose normal is along the negative x direction is what is asked. So we can see that we have the rectangle like that. Yeah, so we have the rectangle like that, and point D is over here on the side surface of that. So what is asked is the magnitude of the stress vector at that point. Now, essentially the discussion of free surfaces is warranted here. So let me just delve into that, what a free surface is. So free surface implies that something is free of traction. That is, it means that traction free. Or we saw traction can also be denoted as a stress vector. So it is because if I say stress free, then it might be a little more confusing whether it is the scalar component that is free or the tensor is zero or stress vector is zero. That is why I'm using the special term as traction, which is just the other name of our stress vector. So traction free meaning that on such surfaces the magnitude of traction vector is zero. It has zero components, and we know that the magnitude of traction is nothing but the square root of the sum of squares of the normal plus the shear stress on that plane. And since both are individually positive quantities, the sum of two positive quantities to be 0 implies that both normal stress as well as shear stresses are 0. So any surface which has the normal stresses acting on it and the shear stress acting on it as 0, that is the absence of normal stress and shear stress on a surface, makes it a free surface, makes it a traction free surface, specifically speaking. Where does traction come in actually? In general, in our strength of materials, we don't essentially go and solve differential equations because we stipulate the displacement field in certain way. But when we go to higher level courses, we will be essentially solving this problem as a boundary value problem. So there we will have to specify the boundary conditions along the boundary. Essentially, we have this rectangle. So along the boundary of this rectangle, I have to specify the boundary condition, how I have applied the loads. So along this boundary, my traction boundary condition I will have to mention. So for that, it is important to understand what a free surface is. It will also come in handy in many other cases where we, some nuances will also be seen when we derive shear stresses and so. But just so we understand, so essentially we are seeing that on this surface, there is no load applied on the left side or the right side for that matter. Even on the top surface, if we see only the hole is loaded, the top surface is actually free of any stress. Bottom surface is also free of any traction, so to speak. So a priori here we can see that at point D, the traction vector is 0. Or if I were to put it like that, Tnx, Tny at point D is 0, where n is this vector. I know that this makes an angle if this positive x is this way. If this is positive x, this is positive y. I know this direction makes an angle 180 degrees. The normal makes an angle 180 degrees with the positive x axis. So n cap is essentially cos pi sin pi, which is nothing but -1, 0. So the traction on this is 0 by the very fact that it is a free surface. It is falling on a free surface. But let us also see how it comes about using our knowledge of Cauchy's formula. So we know from our knowledge of Cauchy's stress formula, we know that traction on any plane or the stress vector on any plane is given by the stress tensor operated over the normal to that plane. Actually speaking, it will be the transpose of the Cauchy stress tensor, but since it is symmetric, it doesn't matter. So this is what traction on any plane is. So now for this plane at point D, I have n as cos pi sin pi, which is nothing but -1, 0. So this I already know. My idea is to find the traction vector. So what I need to find is just the stress tensor. So from the given loading, I know this is a case of uniaxial loading and point D is sufficiently far away from the load points. So at any point in this region, my stress is only along the y direction, which is normal stress. So that much I know. So let this be the this is being pulled by some F. So at any point in this region, sigma xx is 0, tau xy is 0, sigma yy is F by A, and it is tensile in nature, so it is positive. And what is F by A? F is 100 we were given, and area was given to be 40 by 2 or something. So it is given to be 80, which is nothing but 5 by 4 MPa. So therefore, if I were to write the stress tensor at point D, the stress tensor comes out to be sigma xx is 0, tau xy is 0, and then by equality of cross shears I have that as 0 and this as 4 by 5. So this is my stress tensor at point D. I hope we are in agreement with that. And at that same point D, I have my normal given as -1, 0. So from here, what will my traction come out to be at N? Is nothing but this operated over this, which is nothing but 0. So it follows that from physically we can see that there is no traction applied there, either in the form of a shear or a normal stress. That is, we can actually apply load in any way over there, which can be resolved into a normal component and a shear component. Since both these components are absent, the traction vector essentially has to be 0 at that point, which is what makes it a free surface. So from our observation, we already noted that the traction vector at that point has to be 0 along this plane. And from Cauchy's formula also, it follows that the traction vector is 0 at that point. Are there any questions at this point?
Excuse me if I
Yes,
may.
please.
So we have taken force perpendicular to the applied direction.
Yes.
So wouldn't the traction be 0 for the given angle that we have chosen? Wouldn't the traction be 0 for any point within the plate?
Any point.
Yes. So if you consider point D somewhere else, let's say in the middle.
Okay.
So you have the same 0, 0, 0, 5 by 4.
Yes.
Correct. Yeah. And you have the same normal vectors -1, 0,
right.
which means that your Tn would still be 0 at any point. So
what makes this special is that we are essentially looking at the domain boundary here. It is true that at any point inside, if we were to consider the same orientation of n, we will still get our traction vector at 0, but essentially that would come about when we cut it. Why this traction vector becomes important is when we want to define the boundary conditions of the domain under consideration. We have taken a simple domain here. It might be in the shape of a potato or anything else. For solving the boundary value problem, we will have to define our traction along the boundary. That is why this essentially this has been taken, because inside the domain we will not be applying force. We will be applying it on the boundary, and which gets delivered in the form of stress, which induces some stress inside.
Right. So, but if you cut a different plane at a different angle, so I'm just trying to understand how you define your boundaries and why you choose a normal to the surface. Is that how you always do it? Do you only look at the the normal to the surface when you define your boundary?
No, because any component, any force component that is applied can be resolved along the normal and across the normal, which is what we defined as normal and shear components. So no matter how my loading is, when I define it on this plane, it automatically takes care of two components that comes about in defining my boundary condition.
Okay.
Yeah. So I'm just trying to understand what your question is. So if you were to take something like that, you're saying?
Yeah.
Okay.
Yes.
Okay. So why don't we do that, in fact? So for the sake of ease, instead of this point, let me take this point. It is just a mirror image of that. And let me take this to be the normal vector, in fact, now, which is at an angle theta. So now my stress tensor at that point remains the same. Into cos theta sine theta. So my traction components come out to be 0 and 5/4 sine theta. 0 and 5/4 sine theta. Yeah, sounds about right. So when theta is 0, sine theta is 0, it becomes a free surface. It is a free surface essentially, which is traction free for defining the boundary condition. And when I have a normal, that is what I have done here is I have taken this point and I have taken an element like that. I have taken an element like that, and the result says that there is no shear here, but there is my resultant traction is this way. This is what I'm getting as the result. This is 5/4 sine theta. Now, can I? I mean, if you could just ask the question, I would perhaps be in a better position to answer.
Yeah, I mean, I was just trying to understand how this is any different from any other point, and why, how.
The one, it is lying on the surface, so it helps us define the boundary condition for the surface. And for any surface, essentially, when we apply as a when we want to specify boundary condition, that surface will be characterized by its outward normal. Yeah. So if I have a circular this thing, in order for me to specify, in general, we take r theta coordinate system. If this is xy, at any point, in order for me to specify, my normal to the surface will be radially outward. This will be my normal. On this surface, what is the kind of load that I'm applying? The traction that I'm applying is what I will specify, which is why a surface will be characterized by its outward normal. And if it is a free surface, then naturally it will be stress free. I mean, I'm not trying to, I'm not able to tie up what the doubt is. If you could perhaps give me a chance to, if you could articulate it more, I'll perhaps be able to answer you correctly. Yeah.
Sure. No, so I understand that as free surfaces. Okay. I guess. Yeah. No, sorry. I'm not. I'm not able to.
No, that's fine. We'll get it through the discussion. You please, I encourage you to speak out your mind, what it is. Yeah.
Sure. I hope I'm
No,
not
absolutely not.
wasting other people's
No,
and your
this
time.
is the very purpose of this session, actually. Yeah.
Right. So if okay, let me try and get my thoughts straight here. So I have if I have a point in the middle, so if I cut a similar plane, I would get similar results. I suppose the only difference in the free surface is that my shear stress would be zero.
Okay.
I would have zero shear on the free surface
Okay.
because there is nothing else sort of on the outside of the plane
Okay.
considered to take any
All right.
shear.
No, but depending on the loading, even this case, at this point, there would be no shear. If I were to take that same orientation,
Right.
there
Yeah.
won't be any shear.
Yeah. Of course.
Now it begs the question, why are we considering a point on the outer surface and speaking of it as if it was something special, when the same result holds for any point on the inner surface as well for the same normal? That could be one argument.
Yes.
That could be one question. But
Yes.
yeah,
That is
yeah.
my question.
Essentially, what our the you will have to perhaps look at it from the analysis point of view. What we are essentially, this is a simple problem where we know that shear is absent here when we take normal like that. Now, our main idea here is to be able to take a domain, however irregular it may be, specify the boundary condition, and the shear at this point and the stress components at this point is coming as the output of the analysis. That is what essentially what we are doing is we are taking the body and we are trying to solve for the stresses at each and every point in this body. That is our goal of the analysis. For that, what we need to specify is the boundary condition and the governing equations that characterize the stress inside this. So this having no shear when I take a normal like that is the outcome of the analysis. Given that this was a simple problem, you were able to deduce it quickly because it is a uniaxial tension. But in the case of normal three-dimensional problems, we will have a surface, we will have a domain as such. We will be defining, we don't know how the distribution of the stresses are inside the body. So we will be defining the boundary conditions, how our displacements and tractions are defined on these boundaries. And there will be governing equations which will essentially take care of how the distribution is, which is what will be the output of your analysis. Am I making sense?
Okay. Understood. Yeah. No. Yeah. I understand. So basically, you're trying to. Yeah.
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 Any
I think
the
you put it
stress at
rightly.
any point internal to the boundary has come about from the analysis. Why we are studying free surface and traction vectors on the outer surface is so that we can define the boundary conditions, which is the first step to that analysis. You were able to quickly deduce that the shear would be no different at point E, at this point. It will be no different from D based on an analysis because this is a simpler problem. When we go to more complex problem, we don't know how it will vary inside the body. So that will come as part of the analysis. Yeah.
Okay.
Okay.
Understood.
Okay.
Thank you.
Anyway, I encourage you to ask as many questions as possible so that we have an interactive session. Okay, very well. So let us look at this question. I just reordered it a bit so that we have a flow of topics. So this question says there is an assertion that stress tensor at every free outward corner is 0. A reason is said that on a free surface, the stress vector is 0. So let us take the same example as we had earlier. Let this be the case where this was loaded like that. Yeah,
Sorry. Do you mind moving
yeah. I'm so
the
sorry.
pen,
Yes, yeah.
the toolbar? Thank
I'll
you.
move it here perhaps. Yeah. So we looked at that point. Now let us look at this point essentially. Let me take that as the corner and let me blow that up. So I have the corner like that. So that is my corner which I have cut out. I can see that this is a free surface. This is a free surface. That I clearly know. Let my XY coordinate system be defined like that. So this is the normal that characterizes this. Let this be n prime. This is the normal that characterizes this. Let this be n. So from here, we can see that n is 1, 0. and n prime is 0, 1. Also, we know that this is a free surface, what is characterized by n prime. Similarly, whatever is characterized by the plane, by the normal n, is also a free surface. So what does that imply? So we know that Tn is 0. Similarly, we know that Tn prime is 0 by virtue of these being a free surface. Because of the free surfaces, these two are 0. So far so good. Now what I'll do is, I slowly want to move this normal close to that point. In the limit, I'll take it close at that point. Similarly, I'll move this to the right, and in the limit, I will take it to that point. So let us say at the corner, so at the free sharp outward corner, let the stress tensor be given by, presently let us take it generic, let this be sigma xx, tau xy, this will also be tau xy, and this will be sigma yy. Now let us apply the Cauchy's formula that follows. We know, so however, we know that this is 0, but this follows that Tn, from Cauchy's formula we know this is this acting upon the normal to that surface. So this gives us sigma xx tau xy, and this is given to be 0 because of this. So therefore, from this it follows that sigma xx is 0 and tau xy is 0. So this much information we have deduced based on our Cauchy's formula and the knowledge that it is a free surface. Now let us take the other traction. We also know that Tn prime is 0, which implies the same thing, that it will act upon the other normal, which is this. Let me take that here, which gives me tau xy and sigma yy, and this is actually equal to 0. So therefore, this gives us additionally sigma yy equal to 0, because tau xy equal to 0 we have already derived previously. It's a known result, and it is consistent with what we have seen here. So therefore, on the free outward corner, my stress tensor is sigma xx equaling 0, sigma yy equaling 0, and shear equaling 0. In addition to my stress vector being 0, my stress tensor is also 0 on the free outward corner. Now one might ask a question. It would appear that I have taken a convenient example where these two are perpendicular to each other. So it might appear that will it hold good for cases where these are not perpendicular to each other. So let us just take an example like that. Let me take the same case where I have this characterized by n again. Let me move this closer. Only now I will not take this horizontal. Let me take this incline in some fashion. So for this, let the unit normal be like that, n prime, and let this make an angle, say theta, with our x-axis. So again, we can see that these two are free surfaces. So therefore, again, Tn is 0 and Tn prime is 0. Since the normal n still is the same, so whatever results we got based on this still holds. So let me just take that quickly. I know this still holds for this case. Now the only question is on Tn prime. Now n prime is not 0, 1, but it is some cos theta sine theta. But Tn prime is still 0, which follows that my stress tensor acted upon by this should give me a quantity which is 0. So this gives me what? Sigma xx cos theta plus tau xy sin theta. So this is tau xy tau xy cos theta plus sigma yy sin theta. And this has to be equal to 0 because this is a free surface. So this much we know. But from our previous result, we already know that sigma xx and tau xy are 0 here. So let us just substitute that. I am just substituting this information from the other plane which I got. So therefore, so this goes to 0 and this goes to 0. So I just have 0 on the top. Here tau xy is 0. This remains. We don't know anything about sigma yy presently. This is 0, which tells me that sigma yy sin theta is 0. Now this can only hold in two cases where either theta is 0 or sigma yy is 0. But in our case, clearly we have taken a theta which is non-zero. So in the most general case, if this has to hold, case for sigma yy sin theta to be equal to 0, sigma yy has to be equal to 0. So this also shows that all my stress tensor components come out to be 0 on a free outward corner. Now I encourage the viewers to do it for another example. Well, n also is not parallel to x. It might also be oriented. Perhaps you can take something, an example like that, where this is n prime and this is n, which are oriented at different angles to x and y. Let us say this is alpha and this is at theta. I encourage you to solve it for yourself and see that this indeed holds good, that at the free outward corner, the stress tensor actually comes out to be 0. I hope this is clear. Are there questions from anyone else? Please feel free to ask if there are. In any case, I welcome the questions, Mr. Jayakrishnan. I'll perhaps move on, and I'll get back to that question with some, more convincing answer to that. Okay. So the correct tensorial representation for the strain in 3D is given by which of the following is the question. Essentially, what is different between stress transformation and strain transformation is in stress transformation, we had a rotation matrix operated over the stress tensor. And then the transpose of this rotation matrix. So this was what was giving our stress transformation equations. This is how our stress transformation equations were actually framed. When we come to strain transformation, it essentially transforms in the same way, provided tau xy. In strain transformation, this will anyway be epsilon xx, epsilon yy. That is very much similar analog to our stress. The only thing that differs is that our shear strains have to be expressed as epsilon xy, where epsilon xy is nothing but my engineering shear strain by 2. So only when I express it as half of that quantity, the transformation actually holds. However, everywhere, wherever we see shear strain, wherever we see shear stress, what the shear strain it causes is essentially gamma xy only. But if we are to go with our strain transformation equations, if we were to consider this as a tensor, it only becomes a tensor when we have half of these quantities placed here. Because how we define strain is, we have seen how this is defined. It actually is the sum of these two. So when we go for strain definitions, this quantity and this quantity, although it is equal, it is the sum of two sub quantities. That is, when this gets transformed, this is theta 1, this is theta 2. So tan theta 1 plus tan theta 2 essentially makes up for the entire shear strain gamma xy. But this has to be distributed into two components and given to the strain tensor, which is when it will get transformed. So the sum and substance of what I mentioned is that when we write the strain in the form of a tensor, essentially our shear strains are half of the engineering shear strains, which is gamma xy, which is the shear strain which will be caused by tau xy. So I hope that is clear. With that light, just extending this to 3 dimensions, we will be able to see that this is not a tensor because we have gamma xy. Essentially, it should be gamma xy by 2. Should be gamma xy by 2 and gamma yx by 2. But since it is given as a whole, this is not a tensor. This is the tensor. This also isn't. And here we have epsilon and gamma placed in the same matrix. So this is also not a tensor. So the correct tensorial notation for strain in 3 dimensions is this. Are there any questions now? Is it clear? Why we don't need to do this for stress, but we need to do this for strain? Okay. Okay, I take it that it is clear to others as well. If not, please feel free to ask. So the correct tensorial notation is this. So what does this imply? This has a direct correlation on our Mohr's equations, because we had seen that this essentially can be recast when it is simplified and recast as Mohr's circle's equation. What we were getting was sigma x prime minus some essentially sigma average whole squared plus tau x prime y prime squared was giving us some r squared, which was having some formula. Here, when we want to draw a Mohr circle for strain, this will be epsilon. This will be epsilon x prime, epsilon average plus epsilon xy squared, x prime y prime squared equal to r squared, where x prime y prime is gamma x prime y prime by 2. So in our axis of the Mohr circle, for stress, we saw this was tau x prime y prime. Now this will be gamma x prime y prime by 2. That is all the difference there is. Other than that, there is essentially no difference. If we solve a couple of problems, it will become clear. So I just don't want to be repeating the same point and confusing you further. So I'll leave it at that. If you were to solve a couple of problems, it will become clear. Okay, let us look at this question. The figure shows cross-section of a thin-walled pressure vessel subjected to an internal pressure. So we have the pressure vessel like that. And then it is subjected to an internal pressure. This has some wall thickness, which is much lesser than the radius, which is why it is being termed as. So this thickness T, and this has a, let us say, a radius of R. So T is much less than R, which is why this is being termed as a thin-walled cylinder. So consider a point A on the inner boundary. So this is subjected to pressure, internal pressure. And we are considering one point A on the inner surface. So the idea is to populate the stress tensor here in both polar as well as Cartesian coordinates. So let me take that point. I'll just remove this. So let me blow this up. All right. So at this point, we have to first express how the stress element will look like, and we have to identify which are the zero components. Now, can we see that this is not a free surface? The inner boundary is definitely not a free surface because we have pressure applied here. So at every point, the pressure is P along the radial direction. So to that end, I hope that is clear. So if I draw two circles like that, and let this be taken like that. So this is my stress element in the polar coordinate system. Anyway, where this is sigma RR. Similarly, this is an equilibrium, so this will also be sigma RR. Then I have sigma theta theta. I have sigma theta theta. I have blown it up. If I take an infinitesimal element, it will almost be parallel. I hope you can appreciate that. Now, if what will this stress be if it exists? This will be sigma, or rather tau. It is on the theta plane in the r direction. Similarly, I'll have a shear stress like that. Let us say this will be tau in the r plane in the theta direction. And then from equality of cross shears, I know the rest of the two. Now the question, first let us address it in the polar coordinate system. The question asks which of these components are 0. Now we can clearly see that sigma rr is nothing but my pressure P. Why? Because if I take this point, here the normal vector is like that. And my pressure is acting directly in the opposite direction to that normal vector. And since this element is in equilibrium, I have equal sigma rr acting on the opposite side. Now one thing to understand is this face is not the outer face of the, this face is not this face. We are looking at this point, we have blown up a stress element at that very point and we are seeing the dimensions of this are 0. We have just blown it up to see what are the different faces. That is all. So this is not the outer boundary of the cylinder. The outer boundary is naturally free because we are able to see there is no stress there. We are only looking at the inner boundary. At the inner boundary, we have taken this point A and we have blown up a stress element at that point A, which is of dimension 0. We are only looking at the different planes. And on this plane, we can clearly see that sigma rr does exist because of the presence of the pressure. And since this is an equilibrium, on that face also sigma rr exists naturally. Now, if I were to take this again, put it like this, and maybe cut it in half. If I cut the thing in half like this, what will I expose here? This is sigma theta theta that is acting here. I hope you can appreciate that. So this is being subjected to some pressure P. Now this sigma theta is what is balancing out that P. The thickness of this is some T. This is a thin walled cylinder of, let us say, some thickness T. Now from force equilibrium, if this is in equilibrium, if I take sigma Fy equaling 0, what will I get? What is the force, downward force due to this sigma theta? I have 2 of these. So I take 2 sigma theta theta into this thickness, which is T. This is in the downward direction, so I have this as negative. And then on the upward direction, I have the pressure. Now pressure, only at this point it is applied in the parallel to the y direction. Everywhere else it is normal to the surface. But I have to take the vertical component of that. So how will I take? This is nothing but, if I place it here, my vertical component is nothing but, if I take a small element over here, if I take this element, on this element, what will my stress be? P sine theta, and the width of that will be r d theta. And this this will be capital P. So it will be capital P sine theta, which is along the vertical. And this is applied on a strip which is of width r d theta, where r is this measure. R is this radius of the inner boundary. And this I will have to integrate from 0 to pi because I have taken half of the cylinder. So if I were to, so this is the downward force, that is the upward force. There is no other force that is acting here. So this has to sum up to 0 for it to be in equilibrium. So what does this come out to be? So minus 2 theta theta t plus, I'll take PR outside. I just have to integrate sine theta from 0 to pi equals 0. Actually, this has already been solved in the lecture, if you see, but just for the sake of completeness, I'll just complete this PR. So the integral of sine theta is minus cos theta. So I'll take the minus outside. So this is cos theta from 0 to pi. So if we substitute, what do we get? Equaling 0. Sigma theta theta t minus PR into cos pi is minus 1, minus of cos 0 is 1 equals 0. So this follows 2 sigma theta theta t plus 2 PR equals 0. From here, we get an expression for hoop stress, which is sigma theta theta. That is what is called the hoop stress. Is nothing but PR by T. Very well. So we have got one expression for the hoop stress, which is PR by T. Now we are able to see it is not a function of theta. It is just a function of it is a function of the pressure, the radius, and the thickness T, all of which are constant in this problem, which means sigma theta theta at every point is constant along the inner boundary. In which case, this is not 0. So this is also not 0. This is not equal to 0. Sigma RR is not equal to 0. Now coming to the third component in the polar coordinate system, which is tau r theta. Now we can see from the symmetry, let us say that this were to distort because of tau like this. Now the next element to this will be something like that. In that element from Newton's third law, we will have shear acting like this, which means both these shears cancel out. This goes radially around. So from the symmetry of the problem, there cannot be any shear stresses existing in the r theta plane because this circle still remains a circle. Under the action of this pressure, maximum this circle can increase its radius. It cannot get distorted into some other shape because of the symmetry, which is why, and we know that our shear stresses essentially only distort the shape. The shape still remains the same, which is why tau r theta has to be 0. So from here we have identified for the polar coordinate system, sigma rr is not 0, sigma theta theta is not 0, tau r theta is 0 because of the symmetry. Now we have to answer for the other three, which is x, sigma xx, sigma yy, and tau xy. So can we employ some tool that we have at our disposal for this? We can simply transform this matrix. So in the polar coordinate, I have got sigma rr, which is non-zero, sigma theta theta, which is again non-zero, but I have this as 0. These have some value. In fact, why don't I plug in the value also? At point A, my stress tensor in the polar coordinate system is minus P 0 0 PR by T. We have already seen how this has come about, my stress tensor in polar coordinate system. Now using transformations, I know that at point A, basically let me take that figure again. Now point A, so let us say it subtends an angle some alpha. So its normal vector at point A, its normal vector is pointing in that direction. This angle is alpha. This is the normal vector at point A. So far so good. So we want to transform this to the xy coordinate system. So to transform to the xy coordinate system, we essentially have to impart a rotation of, screen is not visible, I'm sorry. Yeah, we essentially have to impart a rotation of minus alpha, right? So what do we know about sigma xx, sigma yy? It will be cos of minus alpha is alpha, sine of minus alpha is minus sine alpha. I'm just applying the same our rotation what we discussed here. In this question, we discussed this. We were converting sigma xx to sigma x prime x prime. Now we already have sigma x prime x prime. I'm just converting it back by imparting a negative rotation. That is all I'm doing, nothing else. This into our stress tensor, which is this. Into the transpose of this. So minus goes here. Will just come here. Yeah, will just come here. So on opening this, we will see that unless we take specific values of alpha, all these components will essentially exist, which can also be seen if I have the element like that. For simplicity, I'm drawing it this way. If I have the element like that, when I transform it, it will be having some shear as well. I'm not qualifying the directions presently. That will be based on the values. But when I transform this into the xy coordinate system, essentially all the three components will exist unless I specifically select some point where it doesn't. For example, if I were to select this point, well, where alpha is 0, there my shear will not exist. But nonetheless, for a generic point which is given in the question, all the three will exist, which means all the three will be non-zero. So sigma xx will not be 0, sigma yy will not be 0, tau xy will not be 0 at point A. So what we have got from this analysis is only that in the polar coordinate system, my shear stresses do not exist because of the problem being axisymmetric for this question. So are there any questions at this point? Is it clear what we discussed? Okay, I take it is clear. All right. Okay, if so this is clear, I'll move on. So let us look at this question. Answer true or false for the statements in one particular fashion. Point A. Option A says if the stress tensor is 0 at that point, then stress vector is definitely 0 for any of the planes passing through that point. Is that true? From our Cauchy's formula again. Because rather than there is no point in maybe knowing this as a statement of fact. We always have our formulae given by Cauchy at our disposal. We can always apply it and see for ourselves whether this is true. So what they are saying is my stress tensor is 0 for any normal which is characterized by the angle theta, my traction along n. This is what they are asking. If the stress tensor at a point is 0, then the stress vector is definitely 0 for any of the planes passing through that point. If I multiply this out, I can see that this holds good. So this is true. The refractive index is a scalar quantity. Now, one might wonder where did we jump to optics suddenly? Essentially, as you would have seen in the lecture, there have been a lot of results from photoelasticity that have been discussed. So that is where this just to enthuse the students about how it comes about. A refractive index is essentially a tensor quantity and it bears a direct correlation with our stress tensor, which is why our stresses are related to the optics, which is the principle behind our photoelasticity. So this might sound as a matter of fact, but this has been discussed in the lecture that refractive index is actually a tensor quantity, much similar to our stress. So it has a bidirectional dependence. In photoelasticity, the model which is birefringent behaves like a crystal when it is stressed. So I'll just give a very small brief about birefringence. So when we have our normal prism, let us say, if there is a light impinging on that, we will have it get refracted like this and then follow the path like that. And we know from our Snell's law that this is I, this is R, sin I by sin R. That was the refractive index. We saw all that. It so happens that there are certain materials where when we impinge this light, it will get split not into just one ray alone, but two rays. It will get split into two rays instead of just one of different amplitudes. So these materials are basically called birefringence. Why? Because bi means two. It has two refractive indices. That is why it is called birefringent. Now, it so happens that there are naturally occurring crystals where this phenomena is observed. The phenomena of birefringence is observed, which means they have two refractive indexes. Only thing is, this light which passes is still along the same direction but travels with a different velocity. It travels slower and it is mutually perpendicular to that light. So that is special about crystals. So as a consequence, without delving much into the optics, I just want to give a flavor of what this entails. So what happens is crystals is this is traveling along the same direction but with a different speed, but slower or faster. So what will happen is there will be a phase lag. Once there is a phase lag, we know that if there is a wave like this, and then if there is a phase lag, we know that it will interfere. It will have some patterns getting formed, which is what we see as our photoelastic patterns. Now it turns out the amount by which it lags, it is directly proportional to our stress induced at that point. So this is true. What we saw here is true of crystals, which are naturally birefringent, which have this property of two refractive indices naturally. There are certain materials which behave like a crystal when they are stressed. That is what makes it very interesting for analyzing stress flow in photoelasticity. So basically some polymers like epoxies, polycarbonates and so on, they have this property that when we stress it, at each and every point, it develops two refractive indices. So when we impinge light on it, it will split into two light vectors, but with different velocities, which will start forming some patterns. And it turns out that these patterns, the phase lag that is there between these light vectors is directly proportional to the stress. So the more we stress it, the more light gets split into two, with the more being the velocity difference, more is the phase lag, and uh, a different color emerges essentially when we impinge light vector. This is explained in more detail because this is a slight detour from our solid mechanics. We will be dealing with crystal optics and so on, then come back here. I don't want to delve much into that. I will discuss only up to the extent the problems warrant, because otherwise we will be going into a whole study on experimental stress analysis, which is already there. A playlist is already there on the channel. So interested people can watch it. I will leave it at this, but if there are any questions specifically to this, I'm happy to take them. Okay. So in photoelasticity, a model which is birefringent material behaves like a crystal when it is stressed. So photoelasticity works on the principle of stress induced birefringence. So if there is anyone not feeling comfortable with understanding this, there is no need for apprehension. This is only a small part uh, of the course essentially, and this is just to enthuse students towards conducting experiments in solid mechanics where we can actually visualize stress. Even otherwise, we will be dealing with the hardcore mechanical topics of stress, strain, and so on. So there is no need for any apprehension. So the most general form of polarization is elliptical polarization. Basically, what this means is if there are two light vectors, what we discussed was there were the light was getting split into two light vectors. If I have two light vectors like that, the resultant of these two will be somewhere over there. So the tip, if if the magnitude of this light vector keeps on changing and the magnitude of that light vector keeps on changing, then naturally this tip is going to move along a path. And the most general path that it traces, the locus of its tip, it basically traces an ellipse, which can degenerate into a plane, which can also convert into a circle based on certain specific inputs. But I don't want to delve much into that naturally, because this is going much into crystal optics and it's a detour from our mechanics. So I will stop there. Most general form is our elliptical polarization. So I will leave it at that. If you are interested, there is also videos uploaded on the same channel on experimental stress analysis. If anyone is interested, I encourage you to go and watch them. So let us move on. Okay. So what we have here is a differential element of material at a point is subjected to plane state of strain. What does plane state of strain mean? So we have, let us say we have the XY coordinate system like that. This is X and this is Y, and Z is coming out of the plane of the paper. There is no strain along this direction is what it means. So any any strain component that has a dependence on the out of plane direction is zero, is what they are implying, and it has been given in the tensorial notation as this with microstrain. Microstrain is nothing but 10 power minus 6. This is just a convenient way of representing 10 power minus 6, because strains, as we see, are extremely small quantities. Okay, so this is my strain tensor. Epsilon ij is given by 400 110, 0, 110, 50, 0, 0, 0, 0 microstrain. Now one thing we must quickly recognize is this is a strain tensor. So 110 is not gamma xy, it is gamma xy by 2. I hope that is clear as we have discussed. So the value of the first invariant, the second invariant, the third invariant is asked. As we discussed in our previous session, what invariants are for any tensor that can be represented as a matrix, it will essentially have three, if it is in 3 dimensions, it will have 3 invariants. Invariants are quantities that do not change with transformations. If I have it in the xy coordinate system, suddenly if I were to convert it into a polar coordinate system by rotating it by some angle theta, these quantities will not change. These quantities are characteristic of that matrix. So this is my strain tensor. So we know, similar to stress, I should say, similar to stress invariants, which was discussed in the previous session. Those who are finding this new can go and take a look at that video. So strain invariants are, the first strain invariant J1 is nothing but trace of epsilon, which is nothing but a fancy term for the sum of the diagonal elements, which is 400 plus 50 plus 0, which is 450. The answer has been asked in into 10 power minus 6. So this is already micro strain. So we need not convert it. So this is just 450. 450 into 10 power minus 6 is also 450 microstrain. It is one and the same. The second invariant, J2, is the determinant of the sum of the determinant of the minors. It is the determinant of this plus the determinant of this plus the determinant of that. So second and third anyway go to 0. We can clearly see that. So we just need to calculate this. So this is 400 into 50, 110 squared, which is 7900. So J2 is 7900 into 10 power minus 6. Since we have multiplied two quantities, it will be minus 12. So 7900 into 10 power minus 12. The exponent is already mentioned here. So it is just 7900. The third invariant is nothing but the determinant of this. We can clearly see since one column or one row is entirely 0, the determinant will naturally be 0. So J3, which is nothing but the determinant of the strain, it is 0. So this is 0 into 10 power minus 18. So now that we have it, now that we have the invariants, we have one way to calculate our principal strains, similar to what we did for principal stresses, using the characteristic equation. So using characteristic equation, which is similar to stress. For stress, it was sigma n cube minus I1 sigma n squared plus I2 sigma n minus I3 equal to 0. So we were getting a cubic equation which will have 3 roots. These 3 roots are the principal stresses. Similarly, we'll do the same thing for strain. It will be epsilon n cube minus I1, which is 450 in this case, into 10 power minus 6 epsilon n squared plus I2 is 7900 into 10 power minus 12 epsilon n minus 0. So I have just substituted I1, I2, I3 for our characteristic equation of the strain tensor. So from here, principal strains come out to be we can solve it using the calculator itself. Minus 415 to 10 power minus 6. This is 7900 into 10 power minus 12. And this is 0. So we get this as 413 into 10 power 4317 into 10 power minus 4, which is 431, nearly 432 microstrain. This is one value. The other value is 18.29, 18.3, and the other value is 0. So these are the three principal strains we have got. Similar to principal stresses, again, we will label them in the algebraically increasing order, which means epsilon 1, which is the maximum out of this, it is this one. Epsilon 2 will be this, and epsilon 3 is 0. So we have derived the principal strains, all the three principal strains for this state of strain. Now what is asked? The minor principal strain in microstrain is what? So which is the least out of these? It is epsilon 3, which is 0. So the minor principal strain is 0. Next, what is asked is the maximum in-plane shear strain is what? So for this, again, as we had discussed for for stresses, for this also we can plot Mohr's circle of strain in 3D. In 3 dimensions. So how do we go about doing that? First, we will have the axis. So I know that this is plus epsilon x prime x prime, similar to my sigma x prime x prime. Only difference is this will be plus gamma x prime y prime by 2. It is better not to write this as epsilon x prime y prime because we will often forget the 2 here, but actual shear strain is this total quantity. It is not half of that. So in order to always remember that, it is better we write it like this as by 2. Okay. So these are principal strains. So naturally these points will fall on this axis only. So the first point is at 432. Let me take this to be 432. The second point is 18. 18. If that is 432, 18 will be somewhere here, let us say. The third is 0. So this is epsilon 1. This is epsilon 2. And this is epsilon 3. So we just need to connect these and we will get the Mohr circle. So this is for 1, 2 plane. This is for 2, 3 plane. And this is for 1 and 3 plane. So we have drawn 3 Mohr circles. And as discussed in the previous session, the region that falls on the boundary of this and inside is the viable solution space for our Mohr circle of strain. That is, any state of strain will be contained in this area only. For this point, which is having the stress tensor like that, which is having principal stresses like this, any state of strain, no matter what transformations we make, will always fall either on the boundary or inside of this shaded area only. That is what this implies. Okay. So for the first Mohr circle, we can see that this is my maximum shear strain, similar to shear stress. Only thing is this is half of that value. This is for 2, 3, and for 1, 3 is for the bigger circle. So what has been asked in the question, let us see. The question asks, what is the maximum in-plane shear strain? Since out of plane is 0 here, what they are talking about is what is the in-plane maximum shear strain. So if we were to consider these two, epsilon 1 and epsilon 2, I'm sorry, this is epsilon 1, not epsilon n, this is epsilon 1. Okay. So what they are asking is, what in the 1, 2 plane, what is the maximum shear strain, gamma xy? So we have to consider this circle. So for 1, 2 plane, we have gamma xy by 2 maximum is nothing but the radius of that circle, which is 432 minus 18.3 by 2. Or in other words, gamma xy max in the 1, 2 plane is nothing but 432 minus 18.3, which comes to 413.7 microstrain. So it must be noted that this is not the strain we should design it for. If it was a design problem, we have to choose the maximum out of these strains in order to design our component. Because just because the third principal strain is 0 doesn't mean that we should confine our attention only to xy plane. So I hope that is clear. Are there any questions at this point? Is it clear what we are discussing? Okay. All right. So the maximum in-plane shear strain is 413.7 microstrain. All right. So a body subjected to a displacement field given by this. This is a vector field, and where x and y are the coordinates, and we have been asked what is the plane stress tensor components and the rotation tensor components. This is what we have been asked. So let us look at what this actually is. So in our analysis of deformable bodies, our idea is to, there are forces and then there are displacements. So force causes a displacement and so on. So essentially we want to relate these two. This can be measured. We want to relate these two. In the case of rigid body mechanics, as we saw in our engineering mechanics courses, we were relating it directly. How we were relating it directly? We were saying that force is mass times the double derivative of our displacements, which is acceleration. The time rate of change of displacement is velocity, time rate of change of velocity is acceleration. So mass times acceleration, we were saying that is the force being applied. But in this was only for rigid body mechanics, for bodies which were rigid, which is again an idealization. So what we instead do is we relate it in an indirect way here. So in the case of deformable bodies, from displacements, we calculate strains. From strains, we can calculate stresses at some point and then integrate that stress all over the body in order to get to the forces. So we take a circuitous route. That is all there is. So basically from displacements to strains, how do we get? There are something called strain displacement relations. From strains to stresses, how do we relate strain and stress? We have been studying from our school. One basic this thing we know is sigma is E epsilon, which is nothing but it is called Hooke's law. We will name it by one more fancy relation called constitutive relation. It is just a more general term for relating strains and stresses in some material. And then from stresses to the forces, we have our equilibrium equations. In the previous session, in the previous week, this is what is derived in the lecture. We have a small element. We put sigma x in one direction. Then we use Taylor series to put sigma x plus dou sigma x by dou x into delta x and then equate it to equilibrium. So this is what we are essentially doing. We were going from stresses to forces and back. Now stress and strain relation, it will come in the weeks to follow. We will see how from strains, how do we relate stresses. Till now we saw what stresses were, how they are defined, how to write it as a component, as a scalar component, how to write it as a stress vector, as a stress tensor, how to transform. All this we saw for stresses. It turns out since these two can be related by an equation, naturally there has to be some correlation between these two, which there is. Strain also happens to be a second order tensor similar to stress. All transformation equations apply here also. So strains are also similar in that nature, which is what we saw today. Now it turns out strain, as we know, we have simply seen it as change in length by original length, which is just one form of the strain. In essence, for a general body which is undergoing some deformation, first of all, we will be calculating its displacements. From displacements, using these strain displacement equations, we will be calculating the strains and then going back to stresses, integrating them to forces. This is how we relate. This is the entire essence of our deformable mechanics of deformable bodies. So it becomes important to understand how from displacement we get to strains. So that is what this question is about. So I will just explain a bit about this. It turns out this strain displacement relations simply put, we can write that in the xy coordinate system, let us say I have a displacement field which is given by u and v. What does this mean? This displacement field means this is a vector field. For example, let us take the same displacement field as given in our question, and I'll try to explain it using this as to what this actually means. This means that there is a body, there is some body, and we have a coordinate system x, y. Since z is not there, I am confining my attention to x and y. So it says, so this point in the body will have some x coordinate, some y coordinate. If I plug that x coordinate and y coordinate into this equation, it tells me what is the displacement of this point under the deformation. So that is what a displacement field implies. So the displacement field is essentially a vector field. So whatever x, y I plug in, it gives me at that point what is the displacement vector like. At this point, it can be this way. At that point, it can be that way. What it implies is the material is getting deformed in, it is having displacement in that way. Now, this can be broken down into two scalar components. This is something I cap plus something j cap. So I have just written that as u and v. So from here we can see that for this question u is nothing but x square plus y square, and v, of course, x square plus y square into 10 power minus 6, and v is 2x y square into 10 power minus 6. So this is something we have been given, we have identified. This is how the displacement field is. Now our strain displacement relation states that it doesn't state, essentially it can be derived, but that is too much of overkill for a single session if I start deriving that. So I will just state it here. It has been derived using our geometry in the lecture, so you can revisit that. What it says is epsilon xx is nothing but my partial derivative of u with respect to x, where u is the I component of my displacement field. Similarly, epsilon yy is dou v by dou y, and epsilon xy is half of dou u by dou y plus dou v by dou x. So there is something called a displacement gradient. Once we have a displacement field, we will take the gradient of that displacement, which is a funny way of saying a time rate of change or a space rate of change. Instead of a time rate of change, we will differentiate it with respect to the spatial coordinates. So that is what a displacement gradient is. So a displacement gradient is defined as this symbol, which is the gradient of the displacement field. Now there might be many symbolisms involved. I don't want to get into that. So this is basically nothing but my dou by dou x operator, dou by dou y. And my displacement field is nothing but u v. So therefore, how we calculate this is by taking this and multiplying it with the transpose of my displacement field. So this gives me, so the gradient of this gives me dou u by dou x, dou v by dou x, dou u by dou y, dou v by dou y. So this is my displacement field, displacement gradient. So let the displacement gradient be denoted by some h. Let h be, capital H be my displacement gradient. So therefore, my capital H is this quantity. It is the displacement gradient. So how my strain is defined is, it is nothing but H plus H transpose plus H into H transpose. So this is how my strain is actually defined. Or this will be rather 2 times of this thing. So yeah, strain is defined like this. But for small quantities, I will ignore this, as this is, I'll just take this to be 0. So therefore, my strain tensor is nothing but this displacement gradient plus the transpose of this by 2. Plus I'll just take the transpose of this. Transpose means I just have to switch the diagonal terms. This by 2. So from here only those relations came about. These relations have come about from here only. I hope that is clear. So this is how strain is defined. Now if we see how rotation is defined, it is h minus h transpose by 2. So that is all there is. So let us solve for how what strain quantities are and what rotation quantities are. So if we see these two will be 2 dou u by dou x divided by 2 will just be dou u by dou x. So the strain is given by dou u by dou x half of dou v by dou x plus dou u by dou y, and it is symmetric. So this quantity will also come out to be the same. And then I have dou v by dou y. So this is my strain tensor. I know how to identify this. The first component is epsilon xx, fourth component is epsilon yy. This is epsilon xy. If this is epsilon xy, I also know that this is gamma xy by 2, which means whatever is inside the bracket is my shear strain. When I take half of that, I am writing it as a tensor. I hope that is clear. Similarly, the rotation which is given by omega is h minus h transpose by 2. So I just have to take this, but I have to put a negative sign instead. So what will this come out to be? Naturally, my diagonal terms will disappear and the off diagonal terms will be same as them except for the sign being negative. Except for the sign being negative. So this is the same. Very well. Yeah. Yes.
Excuse me. Sorry. Would the 2, 1 term be dou v by dou y minus dou v by dou x? Because it is a subtraction, right? I mean, we cannot use equality of cross shears here. Can
All
we?
right. Yeah,
Or
sure.
minus of,
So this will be very well. Is it all right now? Yeah, yeah. So we have the strain tensor and the rotation tensor defined in this way. Now it might be mind-boggling as to why we are doing all this. Basically, in a problem, if you are given that change in length is this much, it is very easy for us to calculate the strain by change in length divided by original length. So that is just for a basic problem. However, we have to graduate to solving more advanced problems also. And in general, when we say that change in length is this much, what we are saying is we are actually saying displacement field is this much. If we say that there is a component which has a change in length along the y direction of 5, what we are saying is u component is 0, z component is constant 5. That is how we are defining the displacement field. So if this is v, we know that epsilon yy is dou v by dou y, which is what comes out to be the strain. So we unknowingly do this. It is just that we should be comfortable if we are given a displacement field, how we should calculate the strain and rotation also. We should be comfortable in doing, which is the idea behind introducing this in the lectures. And this will also be extensively used in the next level courses. So it is good that we get exposed to this. So this I had just stated, and I just went to a slight detour about how this came about. There is much more to this, but that will delve into continuum mechanics, so I don't want to take too much of a detour. So let us stick to what we know now. So what we know is epsilon xx, epsilon xy, and gamma xy are given in this way. Epsilon xy are given in this way. So let me paste that here. This is what we know. And for our question, the body is subjected to a displacement field where u here is x squared plus y squared into 10 power minus 6. I hope there is no problem for anybody in seeing how that came about. It is just this component. And v is 2xy squared into 10 power minus 6. So we have been given a stress tensor A, B, C and D. We know what is A in the xy coordinate system. A is nothing but epsilon xx. So A, so this is A, is dou u by dou x. So what is dou by dou x of x squared plus y squared? We just need to take the partial derivative. So this we can split out. Dou by dou x of x squared plus dou by dou x of y squared, which gives us 2x plus 0, which is 2x. Now we have been given the point where we have to substitute. At point P, x coordinate is 2, y coordinate is 4. So at point P, epsilon xx is nothing but 2x, which is 2 into 2, which is 4 microstrain. Naturally, I missed out into 10 power minus 6. So this will be into 10 power minus 6 microstrain. So under the action of this displacement field, there is a body, and at the coordinate 2, 4, the strain it is experiencing in the x direction is 4 microstrain. 4 into 10 power minus 6 is the strain experienced at that point. This is what it implies. Now what is B? B is my shear strain. So this is my B. So let me take that here. Component B is this, which is nothing but half of dou u by dou y of x squared plus y squared plus dou by dou x of dou u by dou y, dou v by dou x. V is 2x y squared. Into 10 power minus 6. Is there any difficulty for anyone in doing partial differentiation? If there is, please let me know. I will explain it. Because naturally, I don't automatically assume that everyone is conversant in every aspect of mathematics. So if there is any issue you are facing, if there is something not clear about the partial differentiation I'm doing, if there is some difficulty in this dou u by dou x, please prompt now and I will explain it in more detail. So I'll just open this out. Dou by dou y of y squared plus this will just be this. I can simply use the product rule, but I don't want to go too deep. So this will just be 2y squared into 10 power minus 6. So this comes out to be 1/2 of 2x plus 2y plus 2y squared. I'm sorry, this won't be 2x, this will be 0 because we are taking the partial derivative with respect to y. So this is 0, so this is 2y, alright, and then 2y squared. Yeah, this sounds about right. So this is nothing but y plus y squared. So epsilon xy is y plus y squared is what we are getting. So at point P, but y is 4. So this will be 4 plus 16, which is 20 microstrain. Similarly, at what is the value of C? So since strain tensor is symmetric, it will be the same. These two components are the same. And then, so this will also be 20 microstrain. And then at point D, at D, the component D is nothing but epsilon yy, which is this. So let us quickly calculate that. D is this, which is dou by dou y of V, which was 2x y squared, I think. So this leaves us with 4xy. So at point P, epsilon yy is 4xy, which is 4 into 2 into 4, which is 32 microstrain. So let us reflect on what we have done in this question. We were given a displacement field. We discussed why we deal with displacements. From displacement, we come to strain. Then in the next few weeks, we will see how strains are related to stresses. And then we will relate them to force using the equilibrium equation. This is at a point level. Once we have sufficiently understood how this is dealt with at a point by point level, then we will go on to dealing with normal components that we come across in daily life that is generally followed in the strength of material course, that is beams, shafts and columns and so on. So all those will also come, but presently we are focusing our attention at a point. What is happening at a point? How to write the stress tensor, strain tensor at that point, how to get strains from a given displacement field, and so on. So this is how we will calculate the strain tensor. Similarly, I leave this as an exercise for the interested viewers to calculate the rotation tensor. What we will essentially see is, as Mr. Jayakrishan also correctly pointed out, what I had missed out was I simply took this component to be the same, but it won't come out to be the same. Essentially, what we will see is this is the negative of this. So our rotation tensor is essentially skew symmetric. When a matrix and its transpose are negative of each other, it is known as, the matrix is known as skew symmetric. So rotations are skew symmetric tensors, whereas strains are symmetric tensors. So I leave this as an exercise for the viewers to fill how the strain this will come about. Essentially, R and U will come out to be 0. You can work that out and see. S and T will be some value but negative of each other. So from here it follows, which of the statements are correct? The strain tensor is symmetric. Yes. The rotation tensor is skew symmetric. The sum of the strain and rotation tensors gives the total strain at a point. Sum of the strain and rotation tensor gives the displacement gradient at the point. So let us see why that is. We saw that H is our displacement gradient. We said strain tensor is defined as H plus H transpose by 2. And we said rotation tensor is defined as H minus H transpose by 2. So let us add these two. This gives us H plus H transpose plus H minus H transpose by 2. So this essentially gives us the displacement gradient. So this statement actually means something. If we are given a displacement field, it is not necessary that it will always cause strains. It could also cause rigid body rotations. So a sum total of the strains, mechanical strains and the rigid body rotation is what constitutes the deformation or the displacement gradient of that component. So we should be able, given a displacement field, we generally isolate these two components because only this component causes stresses in that body. The other component is just rigid body rotations, what we dealt with in our engineering mechanics course. So the sum of the strain and rotation tensors gives us the displacement gradient at that point. So this is the correct option. So anyway, I've run out of question and near about the time. So are there any questions other than this, what we need to discuss? Is everything clear that we discussed today? Are there any questions from the assignments that you have been attempting? Any doubts from the assignments? Is everything clear there? Okay, so if there are no further questions, perhaps I'll call it a day. Thank you for attending. I'll see you next Friday.
Thank you very much. Good night.
Thank you. Thank you. Good night.